Welcome to Digital Circuits by topNotch Tutorials. In this session, we'll be considering our number systems. So let us consider four number systems, which are decimal, binary, octal, and hexadecimal. In this session, we'll be dealing with binary and decimal number systems only. For better understanding of these number systems, let us consider first our binary number system. And for that, we'll consider a simple example of an odometer as follows.
Let us consider an odometer which is used in our cars to display the distance the car has traveled.
So, talking about odometer, an odometer is a device used to calculate the distance traveled by a wheeled vehicle.
So here we can see a basic panel of odometer. So it's something like this. You'll see the distance the car has traveled. Supposedly, if the car hasn't traveled any distance, it will show 0 on the reading. We are just considering first two digits. And suppose if the car moves by a distance of say 2 kilometers, then the initial digit, the units place digit, rolls to 2. Similarly, if it has gone to 5 kilometers, it will roll to 5. For 8 and for 9 kilometers and so on. But the moment it reaches 9, the first digit rolls to 0 and the second one rolls to 1. And the counting starts from 10, 11, 12, 13 and so on and so forth. In binary counting, we have base as 2, so we have only 0 and 1 as our states. So with these two numbers, we can do a lot of representation. Let us consider only the first bit. Now with only one digit of the odometer, we can represent two states, that is 0 and 1. But once we add another bit to it, initially we had 0, 1. Now we can add two more to it, 1, 0 and 1, 1. So this is how binary counting is done. So with every increasing digit involved, the possible number of states which can be represented are doubled. Like with 2 digits, we can represent 4 states. With 3, 4 2s are 8, so we can represent 8 states. With 4, 16 and so on.
The table illustrates that as the decimal value increases, the number of bits used to express the binary numbers also increases. So in the adjacent table, we can see the relation between decimal and binary numbers. Now for decimal numbers 0 and 1, we see that there is only one bit which is being used to express these values. Now as the decimal number increases, the number of bits used to express these decimal numbers also goes on increasing.
So let us now consider binary to decimal conversion. For instance, let us consider a random binary number 1101. Now in binary we have base as 2. Now let us calculate value of each bit. Like 2 raised to 0 is 1, 2 raised to 1 is 2, 4 and 8 and so on and so forth. Let us consider only 4 bits. Okay, so what this value represents is 1 into 8 plus 1 into 4 plus 2 into 0 plus 1 into 1. If we add this value, we get 8 plus 4 plus 1, which is 13. So 1101 is nothing but number 13 in decimal. This is how we calculate or convert binary number into decimal number. Let us take another example. Zero one 1 0. Now again we'll keep bases 2, which is 8, 4, 2, 1. Okay, so to calculate it, we'll again consider the same procedure. We'll multiply 1 with 0, 2 with 1, 4 with 1 and 8 with 0 and add all of them individually as we did earlier. So it will be 0 into 8 plus 4 into 1 plus 2 into 1 plus 0 into 1, which is equal to 4 plus 2, 6. So 6 is the decimal number whose binary is represented as 0110. We can continue this process for all binary numbers of any length. However, as the number of bits go on increasing, the powers of 2 also go on increasing, and it becomes little tedious to calculate its decimal number.
Now let us consider binary to decimal conversion. The first step would be to write down the number. After writing down the number, we go on to the next step by writing down the powers associated with every bit. So we assign every bit power of 2, which is increasing from LSB to MSB bit, which is 1, 2 raised to 1 would be 2, 2 raised to 2 would be 4, and 2 raised to 3 would be 8. The third step would be to multiply every bit with its respective power, like 8 with 1, 4 with 1, 2 with 0, and 1 with 1. And the last step in this would be to sum up all of these powers to obtain the final answer. So as we can see over here, 1101 in binary is converted or is written as 13 in decimal number system, whereas 110 is written in binary.
Now let us consider decimal to binary conversion. For example, let us consider a simple number like 41. Let's take the number as 41. So for converting this decimal number into binary, we'll have to consider the base as 2 and we'll have to divide this number 41 by 2. So what do we get after we divide 41 by 2 is we get quotient as 20 and we get remainder as 1. Now in the next step, what we do is we consider this quotient 20, we again divide it by 2 and we continue with this process. So 2 divided by 20 is 10 and the remainder is 0. Similarly, 10 divided by 2 will give me 5 and again the remainder will be 0. Now 5 divided by 2 will give me 2 plus 1 remainder. I take this 2 down, divided by 2, which will give me quotient as 1 and no remainder. Now when I approach this step as quotient is 1, it will not give me as this quotient for next division with 2. It will not give me any quotient, but it will give me a remainder as 1. And now this division cannot be continued, so it ends over here. Until we approach to this step, the division is supposed to be continued. First we have to divide the number by 2 with its base because we are considering binary. Then we'll acquire a quotient, take that quotient to the next level and divide it again by 2, acquire another quotient and keep on doing this until you approach this step where the number is smaller than 2, which is only 1. There is only one possibility in binary. So as you approach this step, you will get the remainder as 1. And there you go. Here you have your binary number, binary equivalent of number 41. So this number is considered as MSB and the first number is considered as LSB. So while writing down binary equivalent of 41, we must write it as 101001 in binary. Let us check this answer of ours. Okay. So in decimal we have 41 and in binary it's 101001, 101001. So our answer is right. In this way, we can convert any decimal number into binary.
Now let us consider decimal to binary conversion. Step 1 would be to divide the decimal number by its base 2, then obtain quotient and the remainder. Write down the remainder as LSB. So we are dividing this number 41 by base 2 and we are obtaining a quotient and the remainder. Moving on to the next step, we will divide the quotient in the previous step, that is step 1, and obtain its quotient and remainder. And we will write the remainder as a second LSB bit. So we will take down this quotient to the next level. We will divide it again by 2 and obtain a new quotient and a new remainder. We will keep on having a track of all of these remainders. Remember, the first remainder was an LSB bit. The second remainder was the second LSB bit. And likewise, we will be moving on to the MSB bit. We will continue the process till the quotient is 0 and the remainder is 1. So as you can see, we are taking the previous level quotient and we are dividing it by 2 to obtain a new quotient and a remainder. So we keep on continuing this until we reach this step where the quotient is 1. We take it down to the next level and we obtain a 0 as a quotient and 1 as a remainder. So this one is our MSB and this one is our LSB. So we take the last remainder as MSB and then form the number from MSB to LSB. So as you can see from the previous step, the MSB number bit is the last remainder which we have obtained, and from there we go on forming our complete binary number. So our decimal number was 41 and its binary representation would be 101001 as we have obtained our answer.